viewers, in my last lecture we had discussed disaccharides like maltose and cellobiose in details. I would like to revise linkages in maltose and cellobiose before we proceed further to our today's discussion, that is on lactose and sucrose. So maltose, is also known as maltobiose or malt sugar, is a disaccharide formed from 2 units of alpha D glucose joined with an alpha 1,4 glycosidic linkage. So as on your screens you can see now that we have 2 molecules of glucopyranose, and what we find that there is the anomeric carbon of the first residue reacts with the OH on the 4th carbon of the second residue. That means that the OH on the first carbon of the first residue, which is the anomeric carbon, reacts with the OH on the 4th carbon of the second residue, resulting in the alpha glycosidic linkage. And since the bond is between first and the 4th carbon, we say it is 1,4 alpha linkage. And then what we find that in the second molecule, the OH is facing downwards. That means the configuration here is also alpha. So this molecule is now named as alpha maltose. So this is what you have to remember, is that in this case the glycosidic linkage is alpha, as well as the molecule, as well as this disaccharide is also known as alpha maltose. And this alpha maltose, we call it as alpha because here the OH is at the lower side, that is CH2OH and OH are trans to each other. You have to keep in mind that we are checking the orientation of the CH2OH and the anomeric OH. And which is an anomeric carbon? Anomeric carbon is a carbon which is attached to 2 oxygens. So this is attached to an ether oxygen here, and it is attached to an hydroxyl group here. So this hydroxyl group, which is attached to the anomeric carbon, is known as anomeric hydroxyl group. Now when we talk of cellobiose, then cellobiose is beta glycoside, and this is a diastereomer of maltose. That is, it differs only in stereochemistry at the anomeric carbon of the glycosidic linkage. What we mean here is that the configuration at all other chiral carbons will be same. Only there is a very subtle difference, that is the configuration at the alpha carbon or at the anomeric carbon of the galactose will be different. So we know that this is disaccharide, which is also known as disugar of beta D galactose and alpha D glucose. So what you find here is that in this case the bond between the anomeric carbon and the oxygen is pointing upwards. That is, the CH2OH and this O are in the same direction. If this is pointing upwards, that means the linkage is beta, and since the bond is being formed between the first carbon, that is the anomeric carbon of the first molecule, which is your galactose residue, with that of the 4th carbon, the hydroxyl group on the 4th carbon of glucose, we name it as alpha -4, which indicates that the bond is between the first carbon and the 4th carbon. And then we are naming it as beta. Why beta? Because the bond is facing upwards between the anomeric carbon and the acetyl ether linkage here. So why am I stressing so much here? You have to remember that when I say this cellobiose is a diastereomer of maltose, what do we mean by that? That the molecular formula would be same and the structural formula, when we talk of the structural formula in the cyclic form at the anomeric carbon, the orientation of OH is different. That is, in galactose, the OH is on the top, that is CH2OH and OH are on the same side. And whereas when we talk of maltose, there the CH2OH and the bond between the C and O, that is the glycosidic linkage, is on the opposite side. So what are they? They are diastereomers, and because of this little difference at the configuration at the anomeric carbon, that is the glycosidic bond is different, the properties of cellobiose and maltose are very different. So they can ask you a question as to what is the difference between maltose and cellobiose. So the basic difference that you are going to say, remember, both of them are disaccharides. You can also say that both of them are double sugars. We also call disaccharides as double sugars because they are made up of 2 units of monosaccharides. So where does the difference lie? The first difference lies that these are, that is, in this case we have a difference, that is the glycosidic linkage is different. That is, in case of maltose we have alpha linkage, whereas in case of cellobiose we have beta glycosidic linkage. And the second thing which you have to remember, the units, that is the monomer units are also same. That is, in both cases we have glucose units. The difference is, that is, the difference is between only at the glycosidic linkage, right? So what do we say? That cellobiose has beta 1,4 glucosidic linkage. Why are we calling it as glucosidic linkage? Because here the glycosidic bond is between 2 molecules of glucose. And this linkage is in contrast to that of linkage in maltose. In maltose we have alpha linkage. So the linkage is different. That is, in one case we are having beta linkage and in the other case we have an alpha linkage. So as you can see here on your screens again, in maltose we have an alpha linkage. So what is our alpha linkage? CH2OH and the bond between the C and the O, they are on the opposite side. Or if they ask you which is sometimes a question is asked on linkages. So what kind of bond is this? Is it alpha or beta? So what you have to remember, if the bond is facing downwards between carbon and oxygen here, that is the acetyl glycosidic bond here, then it is the alpha linkage, and if it is pointing upwards, then it is the beta linkage. And this is the only difference between maltose and cellobiose. They are diastereomers of each other. The basic units in them are the same. That is, maltose is made up of 2 molecules of glucose. Similarly, cellobiose is also made up of 2 molecules of glucose. Now we know that the 4 important disaccharides are maltose, cellobiose, lactose and sucrose. Now picking up the string from here, I would like to discuss lactose and sucrose with you in today's lecture. What is lactose? Lactose is a milk sugar. It is also known as milk sugar. Why is lactose known as milk sugar? Because it is present in milk of mammals. As you can see, it is present in milk and all the products which are obtained from milk, like it is present in cheese, it will be present in curd, right? And when we talk of lactose, you have to remember that the monomer units or the sugar residues in lactose are beta D-galactose unit and D-glucose unit. We have not specified whether this glucose unit is alpha or beta, because here the orientation at the anomeric carbon may be different. In this case, the OH is on the top. So if the OH is on the top, that means this is beta glucose unit, and if this OH was pointing downwards, it would have been alpha glucose unit. Whereas this galactose is a beta. We've specified beta here because in this case the OH, the bond between the carbon and the oxygen is facing upwards. So the question here arises, what is the linkage here? Is it alpha or is it beta? The linkage is beta since the bond between the carbon and the oxygen of the glycosidic bond is pointing upwards. Now we also call this as molecule as beta D-lactose. Why are we calling this as beta D-lactose? Not because the linkage here is beta. It is because the orientation of OH at the anomeric carbon, that is at the hemiacetal carbon, is on the top. That is CH2OH and OH are on the same side. That means that this molecule is having configuration beta, and therefore we call this as beta D-lactose. What does capital D indicate here? That is, if we refer back to Fischer projections, then in that case OH on the highest numbered carbons in both cases, that is in case of galactose as well as glucose, both of them will be on the right hand side. So what you have to remember, I'll just quickly recapitulate here again. That is, if we are talking of maltose, maltose is a double sugar, or it is a disaccharide of 2 units of alpha D glucose. Whereas when we talk of cellobiose, cellobiose is a disaccharide made up of beta D glucose and alpha D glucose. And when we talk of lactose, here the monomer units are beta D galactose, and in this case what you're seeing on your screens, it is beta D glucose. So here now we are talking of the synthesis of lactose. So when we talk of synthesis of lactose, I have already explained this reaction in one of my previous lectures, that when we synthesize disaccharides or polysaccharides or oligosaccharides, and you know disaccharides are the simplest examples of oligosaccharides, then this is a condensation reaction. That means a water molecule is eliminated during the course of reaction. So what you have to remember in this case, please remember this, that it is the OH, that is the anomeric OH of the first residue, which will react with any of the OHs of the second sugar residue. That means this OH can be the OH on the fourth, or in case of sucrose you will observe that the reaction is between the 2 anomeric OH groups. So what we find here, that this OH is eliminated as hydroxyl group. I will not go into the detail of the mechanism because we've discussed that previously, and this OH and H from here will be eliminated as water molecule. And then what we have, it results in the formation of a glycosidic linkage. So when this OH is removed under acidic medium, we get a carbocation here, and this oxygen now acts as a nucleophile, and a bond is formed between this oxygen and the carbon, resulting in a glycosidic bond here. And what we find, we have a beta bond here. I am stressing again and again on these linkages, the orientation of this bond, because these are the questions which are normally asked in NEET exams, and this is where you have to be very careful when if they ask you a question, give the preparation or how is lactose synthesized from the monomer units. This is how we have to show that this is the beta glycosidic linkage here. If you make it alpha, then the your answer would be wrong. So you have to be very careful about this linkage. That is, this bond is pointing upward. So this is beta glycosidic bond. But here what we have is, this is the alpha enomer. That is what I mean by here is it is the alpha enomer. That is, in glucose, the orientation of CH2OH and OH are opposite to each other. Since they are opposite to each other, that means this is the alpha enomer. So now the name of the molecule would be alpha lactose, right? So why is it alpha lactose? Because the orientation of OH at the hemiacetal carbon is downwards. That is, CH2OH and OH are trans to each other. But where if the question is asked on the linkage, then please remember linkage is beta glycosidic linkage, beta 1,4 linkage. So the next thing is, you know that this reaction is reversible. So we know that this molecule, if we carry out the acid hydrolysis of lactose, we will get beta D-galactose. So what do we mean here by saying beta? You know that the orientation of OH in galactose molecule at anomeric carbon was beta, that is CH2OH and OH are on the same side of the ring. Capital D indicates the configuration, small d indicates that the molecule is dextrorotatory. So the bond is being formed between beta D-galactose and D-glucose. D here is the, again referring to the orientation, that is, it's referring to the relative configuration, that is the OH at the highest numbered asymmetry carbon in molecule of glucose will be on the right hand side. This D is indicating that the molecule is dextrorotatory. Then here we have not indicated whether it is the alpha form or the beta form. So depending upon what kind of lactose we have, if we have alpha lactose, then we will say that this we are getting here is D alpha D glucose, and if it was beta glucose, then we will say we are getting here beta D glucose, depending upon the orientation of OH at the hemiacetal carbon. So this is what you have to be careful, because sometimes questions are asked on as to what will lactose give on hydrolysis. So here you can see on your screens again that we've carried out the hydrolysis of lactose. So when you look at this molecule, what you find here, that since this bond is facing upwards, that means the linkage is beta glycosidic bond here, and since the OH and CH2OH are on the opposite side, that means that this molecule is having alpha configuration. So when we carry out the hydrolysis, which can be acidic hydrolysis, or the hydrolysis can be carried out with the help of enzyme lactase in biological systems, when we will get D-galactose, and here we could also write beta D-galactose, and here we are getting alpha D-glucose. Why beta D-glucose? Orientation you have to keep in mind, CH2OH and the anomeric OH are on the same side of the ring, whereas in alpha form the CH2OH and this OH are on the opposite side of the ring. So in this case what you have to remember is that the D-galactose unit is an acetal and D-glucose unit is a hemiacetal, which are linked by 1,4 linkages. So this is here again I am stressing on the point that this linkage here is beta 1,4 glycosidic linkage. So when I am saying this is beta 1,4 glycosidic linkage, this is an acetal. Why is this an acetal? Why is galactose residue acting is present here as an acetal? Because the anomeric carbon is attached to 2 oxygens here. So that means you will at once recognize that this is an acetal. What you have to remember is, what is an acetal? Acetal is a molecule in which the anomeric carbon is attached to two ether groups. So we have a ether linkage here, we have a ether linkage here, which is also known as glycosidic linkage in case of carbohydrates. And this here unit here, which is your glucose residue, is a hemiacetal. Why is it a hemiacetal? You remember that hemiacetal is a molecule in which the anomeric carbon is attached to one ether linkage here and to a hydroxyl group here. So this is hemiacetal. So a question may again be asked here. So basically questions will be asked on linkages. So they will ask you which unit is existing as an acetal and which unit is existing as a hemiacetal in lactose. So what you have to, you'll immediately look into the linkages here. So wherever the oxygen, the anomeric carbon is attached to two oxygens, that will be your acetal residue, and where the anomeric carbon is attached to one oxygen and one hydroxyl group, that will be the hemiacetal residue. So now I hope it is very clear that beta D-galactose residue is existing as an acetal, whereas D-glucose residue is existing as hemiacetal. Now since it is having a hemiacetal, lactose has a free hemiacetal group, so that means now it will show mutarotation and it will act as a reducing agent, that is, it will decolorize Felling's and Benedict solution. Let us go back to the previous slide and look here that when we have a hemiacetal, we have discussed this in great details in previous lecture also, but just to revise that acetals are stable in alkaline medium, in basic medium. They do not undergo bond cleavage. Whereas if a molecule is existing as a hemiacetal, then in the basic medium or in aqueous medium, it undergoes ring opening here. And when it undergoes ring opening here, what we find that this will be converted into a CHO group here. And since we have a CHO group here, what we will find that this molecule will be able to exist in two forms, the alpha form and the beta form, through the open chain structure. So that means it will show mutarotation. And since we have a free aldehyde group here, so that means now it will act as a reducing agent. It will react with Felling's solution and Benedict solution. So when we say it will not decolorize, it will give us a red color with Felling's and Benedict solution. You know, Felling's solution is potassium sodium tartarate and alkaline copper sulfate solution. So this, which is blue in color. So when we will add a sugar to it, which is a reducing sugar, say like glucose, fructose, lactose, cellobiose or maltose, it will give us red color with it. The next point that we have to remember is that the enzyme lactase digests lactose in small intestine to give its units, that is, it gives glucose, D-galactose and D-glucose. But sometimes you've heard that some people complain that they are having flatulence, they are having abdominal pain, or they have vomiting, or they have diarrhea after consuming milk. Have you ever thought, why is this so? This is a genetic disease which is known as lactose intolerance, and this is because of the enzyme lactase. That is, this enzyme lactase is non-functional, and because it is non-functional, it is not able to digest, or it is not able to hydrolyze lactose. And since lactose is not being hydrolyzed, that means it is not being metabolized. So this lactose accumulates in the colon and it gets fermented to generate carbon dioxide, hydrogen, methane and irritating organic acids, which then cause diarrhea, flatulence and vomiting sensation. So here again I have shown this, that this is lactose is present in milk and milk products, and when we consume them, and since lactose is not functional here, it will not be able to break down this to beta D galactose and beta D glucose, so it accumulates there. So for this lecture I had referred to the books of Carey Francis, McMurray Joan, Wade, Claydon and Solomon, and you can also refer to these books. It is very well explained in all these books, but all the concepts are not given in one book, and what I have tried to do to pick up important points from all these books and present them to you here. Thank you.